Hi, this is Jeremiah, and this is Lab 1, studying constant velocity. For this lab, I have overlaid objectives, the first one being studying and understanding Newton's second law, using coding and video capture to examine Newton's second law, comparing and analyzing these results, and then connecting abstract physics ideas into this lab activity. Okay, now let us go over Newton's second law. As you can see, F net equals mass times acceleration, and this dwindles down to velocity final equals velocity initial plus F net over m times delta t. This is the first important equation. Let us go over average velocity equals delta r over delta t. This then goes into final position equals initial position plus velocity times delta t. Now this tells us what Newton's second law tells us. If all the forces, the net forces, add up to 0, this indicates that velocity is constant. And as we can see from this equation, if F net equals 0, this makes this part of the equation 0. It tells us that velocity equals velocity, which means it's constant. Now, this then gives us a hint on how position can be predicted through this equation. And since velocity is constant, it can be easily predicted where a ball will land, and can be predicted through computational data. So for this lab, I used a basketball to roll on a flat ground, as you can see, and then I pushed it from the left to right. These are the constant assumptions of this lab. After I took the video of the basketball, I used Tracker to build a graph, and as you can see, the graph here shows the position versus time of this, and you can see that it goes in this positive, almost linear slope. And these are the constants that I used to do the tracker. For the experimental aspect of the lab, I used CloseScript, and these are the constants or the things that I changed. For example, I changed initial position to be this into the code, and then I used this velocity that I determined from this equation to find velocity. And so what this code does is that it uses this equation and uses the velocity that I inputted to predict where each position will go, what position point will go to. Okay, so these are the two lines that were produced. We can see that both have the same slope, but there is a difference, and this difference is account to friction. Friction, as you can see in the experimental blue line, the video that I took, it's close at the beginning, but then it swerves off. This is account to friction because it affects the path of the ball and the velocity of the ball, so then it makes it go off away from this model position. But what this orange line represents is really the position update formula, because it's based off of that. It doesn't account for friction or anything else. So although they share the same slope, friction does cause it to swerve off. Let us look at other aspects of the lab. So what would happen if the ball was rolled differently? In my case, my ball rolled from left to right, and this made the positive slope because it was going in the positive x direction. But if it was from right to left, this would become negative because the origin would come to the left, negative x direction. Other things is that, does this change the effects of the Newton's second law? No, this still means F net is 0, which means velocity is constant. Is there a possibility to see where the pushes and pulls happen to give a 0 net force? We can show this by normal force and gravity. Gravity is pulling the ball down while normal force is pushing against that, but it cancels out and it becomes 0. Now in summary, this lab shows Newton's second law because first, F net is 0, which means velocity is constant. And since if you roll a ball, it shows from the graphs that has a positive slope, and it has a linear slope. So that means that acceleration is 0, which means force is 0. And from that, we can predict the position of the ball from delta t. This is the end of the lab. Thank you very much. Bye.